In this tutorial, I'm going to talk about microprocessors. So it's a very brief introduction to microprocessors, and my idea is to give you a very brief idea about the building blocks of the microprocessor, and then later in the tutorial I will discuss a little bit about two main architectures that we involved in, Von Neumann and Harvard architecture. Let's take a look at circuit like this. So when you have a hardwired circuit like this made using application specific ICs or ASICs, then so this circuit is designed for a certain purpose, and as long as that purpose is served, we are happy, we can use it. Now what happens is that if the requirements are changed, for example, if you want to change probably the output voltages or probably the function, so when to do different things. So when this requirement change, what we happen to do is we have to redesign circuit, and most cases you need to remove certain components and certain components. Well, it's not that easy when you have PCB like that. So when you have large circuit, so it's total redo. So therefore this is kind of headache, and then people start thinking of different techniques to come up with, rather doing this rework again and again to find different techniques. So that is so microprocessor is one of such solutions. So it's a so what people wanted to invent is kind of general purpose hardware which can do different tasks by doing different instruction. So today when you have microcontrollers or microprocessors, you can change the function of it by changing the program and sending it to the device. So similarly there are a lot of other devices. So one such leading one is PLDs or FPGAs. So those are like logical cells, so you can rearrange by using a program. So in this tutorial we are going to talk mainly about the processors. So usually when you hear the term computer, we always realize some kind of laptop or desktop type personal computer. The real word computer came from Latin term computare, if I pronounce it properly, so that means calculation. So in a computer what you do is you do calculations. So any electronic system or computing system, what we do is we have input and then we do some processing and we send the output. So the same with computing system also, you have input data and then you process it and you send data from the system. So that is what we do. So in today's terms, so computer is a device that takes raw data input from the user and process it under the control of set of instructions. So that is what we call the program, and then produce the output for the future use. So that was the idea of the computer in today's terms. So there's a fun fact in so I think some of you have seen the tables that we use, logarithmic tables. So those tables long ago were constructed using people, and that profession was the person who is doing this calculation and making these logarithmic tables were called computers. So that was kind of interesting. So more or less same thing is done by the computers today. So moving on, so let's talk about what central processing unit is. Now when we talk about central processing unit, there are three components associated with that, out of which the main one is the control unit, so which controls the everything as it implies from its name. And then you have arithmetic and logical unit, so we call it ALU. So it does some of the arithmetic operations and some logical operations, and then together with certain registers with the ALU. So this is basically the processing part in the central processing unit. So ALU together with registers, so they really do the processing, and this processing unit plus control unit, we call it central processing unit or CPU. And so in this diagram, some of the things are depicted with different colored arrows. So you can see if you look at arithmetic and logical unit, it takes input from the control unit or from the main memory, or it might take input from the IO devices or input devices. So there are few things you can see here is that when you see a black wire here, so that is data moving here and there. When you see red wire, that's a control signal. So all these are buses actually, though you can see it's like a single wire. So all these are buses. And one interesting thing you can note here is that a output of the ALU is connected to the registers, and those register set is connected again back to the ALU, so that the input to the ALU could be output from the previous state, that is coming from the register, or directly coming from IO bus, or it could be coming from the main memory. So there are different possible way of inputting data. And also the output, you have registers, and then you can send it to output by IO bus, or you can send it to the main memory. So those are possibilities that you can do. And now when you look at the control unit, it controls more or less everything. So there's a bus coming to the registers, ALU, output, input, main memory. So basically control unit does a lot of controls to the system, out of which some of them are so when you have a data bus or address bus or anything, so always you need to make sure that before transmitting anything, data bus has to be clear. So that is controlled by of course from the control bus. So that the idea of having a control unit here is that it provides timing to the system, and also it provides basic commands like write or read instructions, and also it does some kind of status reporting to in certain cases. So we will discuss later on in different set of video tutorials about those things. When you say control unit, sometimes it's referred as a CU, and ALU stands for arithmetical and logical unit. So now the purpose of this diagram is just to highlight some of the things. So this is more or less the same thing that you have seen in the previous diagram, but it is with less number of wires. So the whole idea is to emphasize on some of the things. So now you can see that this green box is again the CPU. So you have a set of registers, arithmetic and logical unit. In fact, ALU is represented using this type of symbol, and then you have control unit, and from the outside to that you have some kind of main memory. So here it's referred as RAM, but the term is really wrong. So most of the memories today we have, they are RAMs, so it's random access memory, but this is our main memory. There are a few things you can see here. So you have two inputs. So these input, if you remember the previous slide, these inputs could be coming from these output registers, or from the main memory, or from IO bus. So there are different ways of this data is coming in. And so once the processing is done in ALU, result is sent to one of the registers, and whenever this processing is done, the status of the result that will be transferred to the register is reported back to the control unit. So we call it a status reporting, or those are we call flags. And then the type of operation that they need to do and things like that is coming from the control unit, and also control unit controls the registers whether to set or enable. So when you say set, that is reading data. When you say enable, it's sending data from output driver of the register. So let's again discuss a little bit about the ALU, so arithmetic and logical unit. So usually this is the typical symbol used for the ALU, and then you have two inputs. So those are like two operands probably. Then you have output, and also whenever you do any operation, you send status to this control unit. So that some of the examples of those status is that when you do some operation to A and B, so if output, so if there's a carry out, like so you add to 8-bit numbers, and once you add it, the result is 9-bit, so processor can't handle it, so it's a carry out or kind of overflow. So probably there's subtraction, you borrow one thing, so that is again carry out, or probably there's a shifting and there's something going out, so that is also carry out. And then you can have a zero flag. So if the result is 0, so all the bits of the result is 0, so we call it zero flag is switched on. Or then if the result is negative, so again it produces another flag called negative flag. And overflow is kind of carry out, so a special case of carry out. And then parity, whether it is when you do the summation of the output, whether it's an odd number or even number, that can be mentioned to the inform, or the inform to the control unit as a status. So we do this one with different flags. And these inputs, although we represent with one single arrow, so those are buses. So it is A, B and C are buses, so those are parallel buses. Then when you talked about the operations that typically ALU can do, is one major thing is addition. So it's a summation. So when you do the addition is used to take care of most of the operations. For example, subtraction is done with addition. So if you want to do the multiplication, so let's say if you want to multiply something with 5, you can do 5 times addition. So things like that you can easily implement with addition. Then you have the ALU is capable of doing bitwise operations such as AND, OR, XOR, and also NOT. So for example, if you want to get one's complement, so every bit has to be flipped, so that is NOT, bitwise NOT. And also in addition to that, ALU is capable of doing shifting. So when you have bit pattern, you can left shift, right shift by inserting zeros or 1. So all these things are possible with the ALU. So in fact, if you look at the operation that ALU can really do, is basically addition, shifting, and some bitwise operation. So from which we do almost every mathematics today. So now we'll look at some different architectures of modern computers. So one of the most successful architectures was proposed in 1945 by a Hungarian-American mathematician called John Von-Neumann. So his proposed model, this computing model, it's a theoretical model So you need to have a memory containing instruction and data. So when you say instruction, those are the things that you need to do. Usually we call the program, and data is the variable. So in this proposed model, there is a allocated location called memory, where you can store instruction and data. Then you have a processing unit, where you can do arithmetic and logical operations. And then you have control unit, which main purpose is to interpreting instructions. So you remember that instructions are stored in a memory. So the main purpose of control unit is to interpret those instructions. And then you have some input and output system. So those are the main components proposed by John von Neumann in 1945. So his machine was like, so this concept is really interesting concept, and later on it leads to the development of modern computers. So in von Neumann architecture, you can see that you have processing section, it's arithmetic and logical unit and registers. Then you have control unit. So I have mentioned some of the things available inside control unit. One is called PC, or the program counter. That is the instruction pointer. So which instruction to be executed is determined by the program counter. And then there's another register called instruction register. So that is the register. So the instruction recorded in memory is fetched and stored in IR just before executing those instructions. And main feature in this von Neumann architecture is that you have one single memory to store both data and your code or program or instruction. So data is the in terms of program, it's a variable. Instructions are different operations that you do to data. So again, the same things, the properties of von Neumann architecture. So data and instruction are both stored in one single main memory. So memory access by means of address. So when you want to access the memory, there's a one unique address. So from the address you can access that memory. So control unit, interpreting instruction from memory and executing. So all the instructions are in the main memory, and the function of control unit is to interpret. So what to do from this instruction? Should these two operands should be multiplied or divided or subtracted? So those things are decided by the control unit. So that interpretation is done by the control unit, and the real instruction is recorded in the main memory. So, and another feature here is that all the instructions, they are executed sequentially unless it is explicitly modified. So usually if you have 5 instructions, you execute first one, then second one, third one, fourth one, fifth one, sixth one, and so on. But there could be certain cases, so if this condition is satisfied, you execute fifth one. So there could be certain cases. Otherwise, usually instructions are executed sequentially one after the other. And then you have ALU to operate on data. So different operation should be done inside the ALU. And then input and output equipment operation is controlled by the control unit. So that is some idea about the things and their functions in von Neumann architecture. So then in parallel to von Neumann architecture, there's a one leading architecture. It's called Harvard architecture. In fact, this architecture was named after a computer series called Harvard Mark I computers. So because in those computers, Harvard architecture was first used. And So one main difference between von Neumann and Harvard is that in von Neumann architecture we had one single memory space where we store both data and instructions, but in Harvard architecture we store data, those are the variables, and program or the instruction or the code in another memory. So as a result of that, you need to have two different addresses buses to address data and instruction, and also to get data from the CPU and send data from the CPU. You need to have bidirectional address bus, and then in order to acquire instruction, you need to have fetch bus. So you address it so that data available in that address is fetched using fetch bus. So let's slightly compare these two architectures. So when you have von Neumann architecture, you have one single memory space. Compared to Harvard architecture, you have two separate memories. So there are advantages and disadvantages of having single memory space and two separate memories. So advantage is that you just need one memory space, you shared it, so that programmer can decide the memory allocation. Should I define a lot of variables, or my code I need to spend a lot on my code? That you do when you are doing the program. But opposed to that, if you are using Harvard architecture machine, so data memory and program memory, those are two different memories. So before you buying the device, you need to decide how much program memory you need and how much data memory you need. So hardware decide memory allocation. So that is one kind of disadvantage we have when we are using Harvard architecture compared to the von Neumann architecture. And in Harvard architecture, instructions are executed one after the other, because always instructions are stored in one different location. So first instruction, after that you will execute second instruction and third instruction, so that you can do pipelining with this one. So we will discuss what pipelining is later on. So just keep in mind that pipelining is possible with Harvard architecture, but with von Neumann it is not possible, because von Neumann uses the same memory to store instructions as well as the program. So then there are advantages and disadvantages in both architectures. For example, if you are using Harvard architecture, you need to have two different addresses buses and two different data buses. So they are kind of expensive to have. So when you compare to Harvard architecture to the von Neumann architecture, one advantage is that having two different address buses, you can address instructions at the same time you can address memory. So that then having two data buses, you can fetch instruction at the same time you can fetch data. So therefore there are advantages and disadvantages in both architectures. So therefore people start using modified Harvard architecture for different devices. So out of which there are two types of main devices. One is almost von Neumann device. So it's a von Neumann machine, but few tricks have been done just to mimic Harvard architecture. And then we have almost Harvard machines. There are few things that mimics von Neumann machine, so that you can use it. So in almost von Neumann machines, usually what we have is the split cache. So you know that in the so usually when you consider the memories in the computer, you have main memory, so-called RAM, which is kind of fast memory. Then you have memory nearby the processor, some registers. Then you have L1 memory, L2 and L3 memory. So those are what we call cache memories. they are extremely fast compared to so-called RAM or the main memory. So usually these main memories are made out of DRAM. So DRAMs are like kind of a capacitor coupled to a transistor. So capacitor is charged, and that charge capacitor is coupled to the bias of the transistor. So from that you can maintain logic 0 and 1. But with DRAM, one issue is that it's the charge of the capacitor is decaying over the time, so you need to keep on rewriting to that. So opposed to that, in cache memories, usually they use SRAMs. So when you use SRAMs, they are like cascaded transistors, 5 or 6 transistors cascaded. So those type of SRAMs, you don't need to refresh. And so therefore SRAMs are kind of faster compared to DRAMs. So, but the problem with SRAMs are they are like kind of expensive to build, and even if we build it, they are little bit larger because it requires 6 transistors or 5 transistors compared to DRAM requirement where you need only 1 transistor and capacitor. So when you have this cache memory, so usually when you have almost Von-Neumann machine, so L1 cache memory, which is the cache memory very close to the processor, very fast one, you have to split one so that data and program are separated, so that even this almost Von-Neumann machine is running, you can parallelly access data and instruction, so that pipelining is possible with this kind of machines. Then we have 2 different scenarios for almost Harvard machines. So accessing instruction memory as data. So this is one issue with the Harvard machines. So these machines are really Harvard machines, but some of the Von-Neumann flavors are added. So one thing is that if you want to read constant, so constants are usually goes to the program memory. So when you read constants from this one, so there are like dedicated hardware to handle this one. So in almost Harvard machine, one feature is the access instruction memory as data. So instruction memory is in Harvard machine is separate one, so you can't just access this just like the way that you access data. But there are different hardwares are implemented in almost Harvard machines to access instruction memory as data. So for example, constants, we can read constant from program memory. And then another thing is that the other way around, so read instruction from data memory. So this is another important thing. So you have so having this feature, it allows executing code from data memory. So when you have so for example, if you're considering field programmable device, so when you say field programmable device, is that you can program a device without removing from the system, and that new program can be stored in data memory. So from the data memory you can take it and put it back in the program memory. So that if that capability is built in, so it's another type of modified Harvard architecture. So these two, access instruction memory as data and read instruction from data memory, so those are like some features available in Von-Neumann machine. So when those features are added, those are kind of modified Harvard architecture. So we are adding some of the features available in Von-Neumann machine. And also there could be certain Von-Neumann machines, there's a mechanisms like split cache, so that you in Von-Neumann machine you make use of some advanced advantages available in Harvard architecture is added to the Von-Neumann machine. So usually in today's machine, what you see is modified Harvard architecture. So some of these features are built into that machine, but the machine is basically coming from either Von-Neumann or Harvard architecture. So this is a nice sketch I have seen. So here you can see that this Von-Neumann has a plate. In the plate you have code and data. So this cabbage and carrots, you can see it. So both are in the same memory. So you access with one fork and knife. And in the Harvard system, you have code, that is cabbage, in one plate and data in another page. So those are two different memories, and then you can access with this fork and this knife for the data, and this fork and this knife for the cabbage. So it's like you have two different buses to access this one. So it's a kind of nice depiction of the requirement. So with that, I will wrap up this session. So thank you very much for your attention.